Assalamu alaikum warahmatullahi wabarakatuh. You are welcome to another episode of our online classes. Now, before we continue from where I stopped the other time, I would like to give the solution to the assignment that I sent to you. Now, even though only one of you solved the assignment and forwarded the solution to me, so I'm still expecting others, or some of you to do the same. Now, I gave you three different questions. So let's quickly go through the three questions. Question one. If the applied force acts perpendicularly to the direction of motion of the body, if the applied force acts perpendicularly to the direction of motion of the body, explain in a simple time how work done is affected. Explain in a simple time how work done is affected. Don't forget, for work to be done, by a body, force must be applied, and the body on which the force is being applied must cover a certain displacement of distance. So where so question one, that is, so don't forget we have work done equal what? Force times distance, or force times s. So the unit is joules. But based on this question, we have a situation in which this expression holds when a body is moving on a rectilinear, is under the rectilinear motion. That is, the application of force is in such a way that is parallel to the direction of motion of the body. For instance, I have a table in front of me and I'm pushing that table forward. The direction of my force is forward, so the table is also going to move in what? In that forward direction. So when the body is moving, it's under the rectilinear motion. So the applied force, the direction of motion of that body will be in the direction of what? Of the applied force. But the situation whereby the applied force is acting at a certain angle to the direction of motion of that body. In this case, let us know I have a box on the ground, or a crate of bottles, and I have the applied force acting in this manner at this angle, which is theta degree. So I have the applied force here. Then don't forget, because the applied force, you are going to use this force to pull this box in what direction? In this particular direction. So the direction of motion of this box will be, so our s, the direction of s, that is distance cover, will be in that manner. So it's possible for us to have the applied force in that manner. By the time we now have in that manner, are you still expecting us to have the same expression for work done in this case? No. Now, how do you find the expression for work done here? So the first thing we need to do is to resolve our F here with respect to this angle of inclination of the F. We resolve it parallel, we resolve it horizontally. Now you find the horizontal component of this F. We find the horizontal component of this F, so we have Fx, the horizontal component, equal Fx equal F cos theta. Fx equal F cos theta. Fx equal F cos theta. Now, so because the force that is going to make this box, the work done on this box, that's going to cause this box to change its position from here to another point here. So that work is now given as F cos theta times distance s, which I can write as F times distance cos theta. F times distance cos theta. Now, that is on one hand. What if the applied force is acting in such a manner that the angle of inclination of the force, is vertical? That is, the force is acting on a vertical component, is acting vertically. Okay, let me look at this. Let's first look at this. This is the vertical component. Then in this case, our F, the angle of inclination of F is to the vertical like this. It's not horizontal. So let's say we are having theta there. Instead of this place, we are having theta. And we expect that this box, the work done by this force on this box to cause this box to move from here to here through this certain distance S. Now, should be the force that is going to parallel to this distance. It should be the force that is going to what? Parallel to this distance. So what do we now need now? What we need in this case will be that we try to resolve this theta horizontally. But resolving this theta horizontally, you convert this to the right angle triangle. Then we have this to be alpha. Don't forget, this if this place is 90, so you can easily find the value of this alpha. And in this case, resolving this f with respect to this theta horizontally. Now, using this theta and this f horizontally, so I will have my fx here to be equals to, this is opposite, fx is opposite to this angle. This is hypotenuse. Using SOHCAHTOA, opposite hypotenuse. That is so sine theta equal opposite over hypotenuse. So in this case, I will have f sine theta. Now, if the angle of inclination of the force is inclined vertically to the vertical axis, then my fx is f sine theta. As against when we have angle of inclination to the horizontal, where we have fs to go f cos theta, the work done along that direction is fs cos theta. But in this case where the f is inclined to the vertical with this angle theta, we have f sine theta. So work done by this, work done here will now be w equal fs sine theta. fs sine theta. fs equal f times s sine theta. f times s sine theta. f times s sine theta. f work done equal f times s sine theta. Now, that is for when the angle of inclination of us is to the vertical. But what if we've not answered what the question is asking us? We've not answered the question, but we are heading to that. Now, the question says that applied force acts perpendicularly to the direction of motion. Yes. In this case, what the question is telling us is that we have a box, and the direction of motion of the box, whether we like it or not, will be in horizontal direction like this. We now have our force in such a way that it's acting perpendicularly. F is acting perpendicularly like this. So, which means the angle of inclination between F and distance is what? 90 degrees. Now, come to this, where we have angle of F as inclined to the horizontal. As inclined to the horizontal. We won't use sin theta because it's inclined to the what? Horizontal. That is fs cos theta now. We use fs cos theta. But the angle of inclination here is what? 90. Then my f times s cos, my theta is 90. Then cos 90 will give me what? 0. So therefore, work done by the force that is acting vertically or acting perpendicularly to the direction of motion of the body will now be 0. Will be 0. So the implication of this is that if we have a certain object on the floor and I'm trying to applying force on that object, pushing it down. For instance, I have a big stone. Instead of lifting that stone up, I'm now pushing it down. The work done I'm doing will be what? Be 0, because that stone will never go anywhere. No work will be done on it, and it has been proven mathematically as that the work done by that force, because it's perpendicular to the what? To the direction of motion of that object. So we have cos 90, W will not be what? Be automatically 0. So that's the answer to question 1. So the simple explanation for that is that the work done is going to be affected in such a way that the work done by that force will be 0. Question 2. Question 2. A body weighs 0.48 in air, 0.32 Newton when fully immersed in water, and 0.25 Newtons when fully immersed in a liquid. Calculate the Roman figure 1 lost in weight in water, its relative density, and the relative density of the liquid. Its relative density and the relative density of the liquid. Now, this question is under the density and relative density of a body. So don't forget, the relative density of a body is the ratio of density of that, the ratio of the density of the body to the density of equal volume of water. So let's see what we are given in that question too. We are given the weight in air. Weight in air is also called the true weight. The true weight of that body, and that equal is 0.48 Newtons. We are also given weight in water. That weight in water, weight in H2O, that we call it apparent weight. Apparent weight in water is 0.32 Newtons. Then we are also given the weight in a liquid. So weight in another liquid, which is not water, and that gives 0.25. Now, before I proceed, you should expect that anytime you have an object measured in air, and the same object is measured in water, the weight in air will be more than the weight in water. Why? Because in water that you submerge that object, there is going to be an invisible force called upward force, otherwise known as upthrust, that's going to act on that object, thereby pushing that object upward. That's why we call it upward force. So V is going to make the value of the weight of that object to be less or lesser than its weight in air. So in this case, the concept is to calculate loss in weight in air. Roman figure 1. Roman figure 1. How do you calculate loss in weight? Loss in weight in air. Loss in weight in air is what we call upthrust. Is what we call upthrust in upthrust. Sorry, loss in weight in water, not in air, in water. That's upthrust in what? Upthrust in water. And our upthrust U is given as true weight minus apparent weight, which you can also use density of the liquid. The liquid we have here is water multiplied by volume of the object in mass multiplied by accelerated to gravity. But mind you, we are not using this one for now. The one we are using is this. So our ultra will now be true weight. Our true weight is what? 0.48 minus the apparent weight, which is 0.32. If you use your calculator to do this, so we are going to have a 0.16 Newton. Don't forget the unit. 0.16 Newton. 0.16 Newton. 0.16 Newton. So let's look at Roman figure 2. Roman figure 2. What is Roman figure 2? Relative density of the body. The relative density. The relative density of the body. And how do you calculate the relative density of the body? The relative density of the body is given as weight. The relative density of the body is given as weight in air over weight in equal volume of water. Equal volume of water. Relative density of the body equal weight equal relative density of the body equal weight in air over weight in equal volume of water. Now, this is going to give me what is weight in air. The weight in air is 0.48 Newton. The weight in equal volume of water. What is the weight in equal volume of water? The weight in equal volume of water is 0.16 Newton. 0.16 Newton. So our answer here will be 0.48 divided by 0.16. So we have 0.48 divided by 0.16. 0.16. We have 3 with no unit. We have 3 with no unit. So let's calculate for Roman figure 3. Let's calculate for Roman figure. This is question 2. So let's calculate for Roman figure 3. Roman figure 3. Oh, let's calculate for Roman figure 3. Let's calculate for Roman figure 3. So the Roman figure 3 says the relative density of the liquid. So the relative density of the liquid will be upthrust. Will be upthrust in liquid over upthrust in water. Upthrust in liquid over upthrust in water. So upthrust in liquid will be 0.48 minus 0.25 over 0.48 minus 0.32. This is upthrust in liquid and this is upthrust in water. So if we find this is going to give me 0.23 and this one is going to give me 0.16. So the relative density of the liquid will be 0.23 divided by 0.16. That is 1.44. 1.44 with no unit. 1.44 with no unit. 1.44 with no unit. So let's go to question 3. Let's go to question 3. Let's go to question 3. Question 3. Question 3 states that a piece of copper material of mass 33 grams at 300 degrees Celsius is placed in a copper calorimeter of mass 70 grams containing 62 grams of a certain liquid at 30 degrees Celsius. If the final steady temperature of the mixture is 50 degrees Celsius, calculate the specific capacity of the liquid if the heat losses are negligible. Specific heat capacity of copper is given to be 399 joule per kg per Kelvin. So in this case, what are we given? We are given mass of the material to be 33 grams. To convert this one to kg, that is 0.033 kilogram. Then we are given θ1, that is the temperature of that material, initial temperature of the material, that is 300 degrees Celsius. We are also given the mass of calorimeter. Mass of calorimeter to be 70 grams. To be 70 grams. Mass of calorimeter to be 70 grams. So theta 1, initial temperature of the material to be 300 degrees Celsius. Then mass of calorimeter 70 grams, that is 0.07 kg. We are given mass of the liquid 62 grams, 0.062 kg. And then theta 2, that is the initial temperature of the water and calorimeter. Sorry, not water, the liquid. The initial temperature of the liquid and the calorimeter equal 30 degrees Celsius. 30 degrees Celsius. And the final temperature of the mixture. The final temperature of the mixture, that is the material and the liquid, is given to be 50 degrees Celsius. Then we are now looking for the specific heat capacity. Specific capacity of the liquid. And that specific capacity of the liquid is given as Cl. So let's take it as Cl. Cl. Don't forget the specific capacity is divided by C. Then from here, using the principle of mixture. The principle of mixture says that the heat lost by material. What we need to consider here is that in this principle of mixture, where we heat a particular object, we transfer that object to a calorimeter containing a certain mass of water or any liquid. Now, by the time we transfer that hot object, what is going to happen? There is going to be exchange of heat between that object and the liquid inside the calorimeter. So, at a particular point, they are going to reach the same temperature, and that same temperature is this final temperature, 50 degrees Celsius. At this particular point, we call it the equilibrium, they will reach the thermal equilibrium, in which the temperature of that hot body equal the temperature of the liquid inside the calorimeter and the calorimeter. So in that case, it means that the amount of heat lost by that hot body must equal to the amount of heat gained by the liquid. Now, if we still consider the calorimeter as another parameter in that experiment, so the calorimeter will also gain some part or some certain amount of heat. So the total heat lost by that hot body will be equal to the heat gained by the water, by the liquid, and by the calorimeter. So from that principle, I will now have this equal heat gained by calorimeter plus heat gained by the liquid plus heat gained by the liquid. Now, from the knowledge of specific capacity, we have that H equal mc theta, or change in theta. So heat gained by the material will be mass of the material times specific capacity of the material times change in temperature of the material equal mass of the calorimeter, specific capacity of calorimeter multiplied by change in temperature of calorimeter plus mass of the liquid, specific capacity of the liquid times change in temperature of the liquid. So in this case, we substitute all these parameters and let's see what's going to happen. Mass of the material is 0.033. Specific capacity of the material is what? Now, because that material is made of copper, yes, copper. We have been given a specific capacity of copper to be 399. Specific capacity of copper has been given to be 399. C of copper is given to be 399 joule per kg per Kelvin. Because that material is made of copper, so we use the specific capacity of copper. So we have 399. The change in temperature of that material will be theta 1, initial temperature of the material, theta 1, minus the final temperature of the material, that is theta 1 minus theta 3, equal mass of calorimeter is 0.07 times specific capacity of calorimeter. Because that calorimeter is copper, then I use 399 as well, times change in temperature of copper. Change temperature of copper will be the final theta 3 minus initial temperature of calorimeter and liquid theta 2. That is theta 3 minus theta 2 plus mass of water. What is mass of mass of the liquid, which is 0.062 multiplied by the specific capacity of the liquid that we are looking for, multiplied by change in temperature of the liquid. But don't forget the change in temperature of the liquid will also be change in temperature of the calorimeter, equal theta 3 minus theta 2. Now, in this, we can substitute all these parameters and find the final answer. I will have, if I solve for this side, put theta 1 here and theta 3 there. I will have, for this side, I will have 329.3291.75 equal theta 3 is 50 minus theta 2, 30. That is 20 times this will give me, that one will give me 558.6. Then plus, if theta 3 is 50 minus theta 2, that is 30. That is 20 minus this. Sorry, 20 times 0.062. That is going to give 1.24 Cl. Then from here, we're trying to make our Cl the subject of formula. Making Cl the subject of formula, we have making Cl the subject of formula, that is 1.24. So making Cl the subject of formula, we have, that is, transfer this one to this side. I will have my Cl. This one is plus 1.24 Cl. 1.24 Cl. So Cl will now be 2204.15 joule per kg per Kelvin. Joule per kg per Kelvin. So that is the solution to the 3 assignments I gave you. That is solution to the 3 assignments I gave